Let's continue from the last session where we stopped. I remember discussing how the tautomerism works in acid and basic medium. Let's see the applications for it. The first application includes reactions of alpha hydrogen. The first one is alpha racemization. That means if I take a pure form of an enantiomer which has one alpha hydrogen at least. Okay, this has one alpha hydrogen, making it as a chiral center. That when you react in acidic medium or a basic medium, over the time, the solution becomes racemic. Got it? So, for example, how is this reaction work? Check out. The minute you add it to an acidic medium here, I'm taking acidic medium for reference. This would become OH plus this way and RH R dash. And then H2O will take up the proton from here, push that to make a double bond and move it here. By doing that, we will get a planarity on this chiral carbon as it becomes a double bond. Then we will have OH and H. Now, again when the tautomerization happens, right, that means if H plus is being attacked, correct, if H plus has been attacked here, the H plus can be attacked from either of the directions. That means it can attack from this end or it can attack from this end also. Alright. When will that attack? As the lone pair on oxygen pushes here, the pi bond will push onto this carbon, and from that carbon onwards, you will see there will be movement of bond towards this hydrogen. So it could be above the plane here like this, or it could happen from below the plane. So again, this changes to, okay, a chiral center, back to a chiral center with CHO, and this time H could be on the right in the Fisher projection or H could be on the left on the Fisher projection. Got it? So consider if this was an R configuration, the absolute configuration of this chiral center is R, then we might end up getting R as well as S. Both would be 50-50 percentage. Hence, the solution is racemic mixture. Racemic mixture. Another example of a similar kind. Check out. In case. Okay. So in that case, if you have a ketone here, and let's say there is a methyl coming out of the plane here this way. So it is a chiral center. And now, yeah. So in that case, in case if at all we treat it in basic medium or acidic medium, in either of the case, check out what will happen. So in basic medium, OH minus aqueous. So we would get a racemic form. That means methyl would be here by 50% charge and another 50% with methyl here. So 50% and 50%. This is how it will happen. Now see another example. What if we have CHO here, H here, CH3 here, and CH3 here, some deuterium here, and ethyl here. Just to remind you, this is alpha and this is beta carbon. Now, okay, so if that is been treated with OH minus aqueous, correct. So at alpha position, we should see there should be two orientations that is possible, correct. So I will put it again. So this time hydrogen could be on the left hand side here and methyl could be on the right hand side. But this time, although the configuration has changed at these two positions, at this position and this position, that does not make them enantiomers. So these two would simply become pair of diastereomers. So they would be pair of diastereomers. Usually, diastereomers are not necessarily supposed to be 50% each. Okay. And we can't promise on the fact that they'll be optically active or optically inactive. Most of the time, they're optically active only because there is no cancellation as such. So, solution usually remains optically active. Okay. So, these kind of examples you should be able to figure out whenever there is an acidic medium or a basic medium given to them. So I hope all of you understood what is alpha racemization. Okay, right. Now let's understand what is alpha deuteration. Deuteration is about whatever the alpha position hydrogens are present, you're trying to replace that with deuterium. That usually happens when you take either and hard water, correct, heavy water in the form of D3O plus in acidic medium, or you can take it in basic medium like this. So whether you take acidic medium or a basic medium, racemization, I mean the configuration will also change at this position and it will be exchanged by deuterium as well. Okay. So if you compare mechanism wise here, so you would see we have R, R dash, H and CHO. And as you treat this with OD minus aqueous. So first, the planarity will come here. Earlier we discussed it. So we'll get this as double bond C O minus and H. Because it is in a basic medium, I'm only writing the enolate form. And then the deuterium will be approached in the form of ODT here like this. So pi bond can attack from the top or pi bond can attack from the bottom. Hence, you could notice that deuterium will exchange here. Correct? So what do we get here? So we will get this as C double bond O and H. Deuterium is exchanged instead of hydrogen, and it could have both here also this way. So again it forms 50%, 50% because it is a single chiral center, making it a racemic mixture. Okay, so this is typically how the reaction goes. Now, if the question is more emphasized on identifying the number of hydrogens that can be replaced or how many deuterium exchanges are possible, right? The other terminology that you should hear about is deuterium exchange. Deuterium exchange. So deuterium exchange usually happens for a prolonged time. That means if you keep it in a basic medium or acidic medium for a very long time, then all of the alpha positions will get replaced. For instance, in the first case, there are 3 alpha hydrogens here, 3 alpha hydrogens here. All of them will be replaced. So answer is 6. In this case, there are 2 alpha hydrogens here, 2 alpha hydrogens here. So that makes it 4. Here also we have 4. Here you can notice there are 3 on the left and 2 on the right here. So that makes it 5. Okay. In this case, we have 3 on the left, 1 on the right. That makes it 4. Okay. Next, HCHO, it does not even have an alpha carbon. So 0. Here also, we do not have any alpha hydrogen, 0. This one is an enol form now. It is not a keto form. Let me show you how we can write the keto form. So for this, I can write it as double bond O with this way. This is one way of writing. Double bond O this way. Another way of writing. And this way. These are 3 different enol forms. Okay. So suppose At this position, first a negative charge will be generated when you react with OH minus. Correct? So imagine getting a negative charge here like this. Double bond O and this way. Then definitely it get exchanged by deuterium. Okay. And this happens two times. So imagine I have D2O here. So in that case, it get exchanged by deuterium here. Double bond O like this. Now imagine it is happening one more time with OH OD minus. Again, hydrogen will be relieved out. So you'll get minus, but the deuterium will still be at the same position. So the other hydrogen has released, and this is how it would be. And again, when you react with D2O, you'll get both the deuteriums on it. So we have two deuteriums here, double bond O here, this one. And this, if it gets tautomerized, you will see one deuterium will be left here and the other one will go OD here like this. Correct? This is the way it will happen. Got it? So minus will take D and one more time minus will come as long as there are hydrogens present. So both two times D after coming, then the tautomerism will happen to get into this form. Imagine the same thing you're doing it for this side and this side also. So after prolonged time, at all these positions, hydrogen will get exchanged. And if I write the final product in the phenolic form, I will have one deuterium appearing here, one will appear here, and one will appear here. So total four. Total four exchanges are observed. Clear? See, J, I have written it already. So what does that mean here? Suppose if at all I react this with OH minus, sorry, OD minus, OD minus. So this OD minus will take H plus from here. So that makes it CH2 minus, then CH, double bond CH and CHO. Okay. And then it will take H plus, D plus, and you'll get CHD, CH2D, CH, double bond, CH, and CHO. Imagine doing this for 3 times now. So that means after 3 moles, correct? So I'll write 3 arrows here, correct? So 2 more arrows here. And then after 2 more arrows here, so we'll get this as CD3, CH, double bond CH, CHO. Now see this interesting fact. Once you get this form, now this time the tautomerism would happen where you will have OD minus is taking up this D and you'll get this as CD2 minus and CH double bond CH and C double bond OH. So I can make this into resonance stabilization like this. So on doing that, I will get this as CD2 double bond CH and CH minus. Correct. So imagine because you're keeping it for a prolonged time, at this position again, minus will take deuterium. So as it takes, what do we get? As it takes deuterium, correct, you will get this as CD2 double bond CH, CHD and C double bond OH. Okay. So that makes now this hydrogen also at the alpha position. Okay. So OH minus or OD minus here. So OD minus here. So that will take this H plus, making this as CD2 double bond CH and CD with minus and C double bond OH. Again, if you take react with D2O, C, CT2 and C double bond OH. Correct. Now it will get tautomerized. CH. And eventually, as it gets sort tautomerized, you'll get this as CD3 here, CH double bond CD here, and C double bond OH, correct? Which is same as the first structure. So keep the final form into the first structure case only. But now check out how many deuterium exchange eventually has happened. You got 3 here and 1 here, total 4. So in short, every time you don't have to write the mechanism, all you need to check out is whichever case the carbon is getting a negative charge. So it is becoming a carbanion form. At that locations, always change it with deuterium. All the alpha positions, you change it with all the alpha hydrogens, you change it with deuterium. Okay. So that is one easy way to identify it. Clear? Next, when it comes to I, in this case, there are no alpha hydrogens, so it is 0. Okay, 1 second. Okay, see the next one, K part here. We know at these two positions the deuterium will exchange at this position also, but unfortunately here there is no deuterium here. So what do we write here? So we will write this as OD, and here we'll write one D, here we'll write one D, and here we write only CH3, because at this position you will not be able to see any exchange happening. Okay. Next, look into L here now. So in the case of L, we will have see double bond here, double bond O, double bond here, correct? And we have CH3 here, correct? This is one way I can keep it. Notice this carefully. This is one way of writing the keto form. I can write in 3 different forms. This is one way. The other way I can write the keto form is double bond, double bond, double bond O and CH3. This is another way of writing. Or I can write this as uh, double bond, double bond, double bond O, CH3. Correct. So the regular positions, you know that here, here, and here. That means these 3 positions, the exchange is anyway going to happen. But notice this particular carbon also now. As you react with OD minus, it could actually take this H plus also, and through resonance, it can push it to C double bond O also. That means like this, and like this, and like this. So that means these hydrogens will also consider to be the tautomeric hydrogens. So hence we will get this as O minus, double bond, and double bond CH2 this way. So since you are getting a negative charge here, so eventually what do we write, everybody? We know that after a prolonged time, write this, after a prolonged time, after prolonged time, all of these positions where negative charge is coming, they will get exchanged. So I will get this as OH, H, sorry, deuterium, right? OD, okay, D here, D here, D here, and C with D3 here. So this is what you will get as the final product. So how many exchanges we had? 4 plus 3, 7. So total 7 exchanges has happened. Done. So given any scenario, you please check out how many number of times you can keep pushing the alpha groups with a carbanion form. So as long as carbanion is available at that position, whatever be the number of alpha hydrogens are, exchange them with deuterium. Done, everybody? Right. Let's go to the next one. The next application is about alpha halogenation. Okay, that means at alpha position we are doing an halogenation. Now in this case, acid based mechanism will be different and base based mechanism will be different. So acid catalyzed halogenation, how does this happen? Let's see. So typically, whenever you have an acidic medium, an an aldehyde which can perform tautomerism will give you enol form. I'm sure you remember the mechanism. So here I will get an enol form like this with carbon having this carbon having sorry, the carbon having OH group here like this, because this is H here and this is R dash and R here. So basically, this hydrogen is the one which migrated here. This is the enol form. Okay. And now, when you expose X2 in a polar solvent, it will start showing delta plus and delta minus charge. And the lone pair present on this oxygen will push electrons to get back into keto form. Okay. Sorry, I put the double bond at a wrong position. 1 minute. Let me rewrite that. So this is that OH. This is that OH and H. This is the OH and H. Okay. So the lone pair present on oxygen here, that will push. This will convert into C minus, and that C minus will attack X. Remove this X from here. So what do I get? I will get this as R dash and R, and we'll get this as X here with C double bond OH. Okay. So both things could happen here. Okay. Just a second. Sorry, please check this. So X could get added up here, and again that X could be added up from both ends, from the top also and from the bottom also like this. Hence, again I'll get 50% and 50% racemization. This time alpha hydrogen is replaced by halogen. Okay, correct. Now here is the interesting deal. What if I keep pushing, if there are more number of hydrogens, just like how it happened in deuterium, will all the hydrogens get replaced by halogens? That is a question we need to answer. So let me take this example. I have CH3C double bond OH, and then I'm using X2, where X is chlorine, bromine, or iodine, correct? Sorry, this is CH2CH3. I'll take this one, and now I'm treating that in acidic medium like CH3COOH, but I'm taking this part in excess. But what has been noticed, even after the prolonged time, it has been observed that only one halogen has been replaced here. Okay, that means only one hydrogen has been replaced here. Although there are two hydrogens which could have been replaced, but only this one has found to be major product even after prolonged time. Even after prolonged time. Now there is something happening in this case then. See, problem what is happening here is when you have the enolate form, I mean enol form here like this. Okay, so imagine we have OH and H here, and then we have ethyl here because this is where the double bond is forming. So there is a, sorry, methyl here. So we have methyl here and X here. Imagine after the first case, this one, if you write it in the enol form, this is what you will get. Hmm? This is the enol form. Now, problem what is happening, if this enol has to occur, the lone pair, I mean, there are lone pairs present on halogens. Halogen by nature has a minus I effect, correct? So because of this minus I effect, as well as this double bond can go in conjugation with the empty orbitals of halogen. Okay. So instead of making into an enol form where it can eventually become ketone, now this pi bond will not be forming to a larger extent. So it will always stay in this keto form, but does not convert this into an enol form. So I can say that here now as a note. So the form, enol form from alpha halo carbonyl compound in acidic medium is hardly stable, as halogens are strong withdrawing groups. So withdrawing groups. So because they are strong withdrawing groups, this is what would happen. Okay. So therefore, here, unless the negative charge does not come here or the pi bond is not sufficiently dense here, we will not be able to make another halogen to get added onto it. That's why even after a long time, we are not able to see this. Therefore, suppose if at all I have a compound given like this, double bond O, and I have given you Cl2 in excess, but I gave you in acidic medium, ACOH. In such case, what is the final product we will report? See, although there are two alpha hydrogens here and two alpha hydrogens here, it would only replace one hydrogen here and one hydrogen here. So this is a major product. Okay, so one at a time, correct? So this side when the enol is forming, only one chlorine. This side when the enol is forming, one chlorine. But multiple chlorines cannot come. Okay, clear everybody? Now notice the ratio here. Suppose if at all I now discuss with the ratio. Suppose if this is compound A, sorry, I'll make it into reactions only. I'll write them as reactions. Please check this carefully. Suppose if I write this as reactions, that ketone is here plus Cl2. I took this as one equivalent or one mole, or this as one equivalent. Then what is the product expected? Product expected would be simply double bond O, only one chlorine here plus HCl, correct? So both will be limiting, both will get over, and I'll get one equivalent of this and one equivalent of this. Similarly, let me write the second condition. Okay. What if I write the second condition? One second. Sorry, check. What if I have two equivalents now? If at all I have two equivalents or two moles here, and chlorine is limiting. Since chlorine is limiting, only one chlorine would come. Still the product will be same, but here one equivalent will only be consumed. So one equivalent will be left over. One equivalent will be left here and one equivalent will be formed here. That's it. That is the product which will get. Next thing, suppose if at all I use the same equation again, put that here, but this time I'm taking excess form, just which I have already done. So which means if at all I take one equivalent here and let's say two equivalent here, then also the reaction will get completely over, but this time I'll get one equivalent of this product, correct? So one equivalent of this product here, correct? Check quickly. Everybody, please check out quickly. So try doing this. What? Just check out what are the products you will get in this case. Okay. So if at all I have it like this, double bond O, methyl here, and I'm treating this with Cl2 excess, right, in acidic medium. So write down what is a product. Similarly, I have CH3, CHO reacting with Br2 in CH3COOH, correct, with two equivalents. Then what is a product? And if at all I have CH3, sorry, if at all I have like this with C double bond O this way, and that I'm treating with I2 in CH3 COOH, clear, of one equivalent. Then what is the product you will get? Please check this out and try figuring out what are the products. Quick. Let's see. In the first case, because I used excess, I can get one chlorine here and one chlorine here. And I told you that we cannot go anything more than one chlorine at one direction. So I can get one chlorine here and I can get one chlorine here. So that is a major product you will get. Now here, even if at all I use two equivalents, it does not matter because number of bromines, that number of carbon hydrogens that you can replace is only one. That is the product. Here I took only one equivalent. So in such case, you need to check out which side is the stable enol form. You can see this side, if I at all I get, that is a stable enol form like this. This is O, OH and ethyl. This one, or I can have O here, right? Sorry, like this. OH with double bond ethyl here. These two are the enol forms. With respect to this alpha hydrogen, you will get this enol. With respect to this alpha hydrogen, you will get this enol. So you can see stability of enol is more here. So this is the stability. So based on that stability, we can say the major product will be based on this position. So hence here when you write the ketonic form here, so I'll get this as double bond O this way with uh, iodine at this position. So that is a major product. Done. This is about how the basic medium works, acidic medium works. Got it? Okay. Right. I'm leaving you with some space. You can practice it once again. Okay. After you take a printout if you need it, or just after writing that, if you still have enough space, just leave it for practice. Now let's see how the base catalyze mechanism works. How the base catalyze mechanism works here. Check. First, when it comes to base catalyze mechanism, let's say I have a chiral center here, R dash, and CHO. And when you treat this with OH minus, okay, which is the rate determining step here. This is the slow process where enolate ion is forming. So R dash with carbon having minus charge here, and this double bond O, H here, and this negative charge would be pushed. This pi bond will be pushed up. So by which you will get this as R dash, double bond here with C, O minus, and H. This is what you will get. And now I have X and X here. So again, this negative charge will close. The pi bond from here will attack, remove this X. So same thing is happening as what we have learned earlier, where R and R with X here, with C, double bond O, H here is happening. Correct? And uh, since the attack is happening on a double bond position, so it could come on either side. So that's the reason why you can get again a racemic mixture. So this I can write it in the form of racemic mixture like this. So CHO with halogen here, R dash and R, or R here, X here, R dash and CHO here. So these two are the products what you can get. Okay. This is base catalyzed mechanism. Now, what is the interesting fact here is, check out, in case if you have multiple number of hydrogens, okay, I'll take this example here. Suppose I have CHO here, and that I am treating with Br2 in the presence of Br2 in the presence of OH minus in excess. So how does this reaction work now? Check out the mechanism. The first step is CCHO. OH minus will definitely take proton from here. As it takes proton from there, you get minus here, CHO. And then we have Br and Br, to which this will attack, and you will get one bromine here, correct, and CHO. So what you need to realize is that this bromine here, I mean at this alpha position, we still have one more H. So again, OH minus will take H plus, makes a carb anion here and CHO. Now listen to this place, because removal of H plus is always the rate determining in such case. So this is R1, this is R2, rate R1 and R2. So in that case, what we can say, at this position, there was not any withdrawing group, but at this position, Br is a withdrawing group. Because of withdrawing group, this hydrogen's acidity will increase. So if you compare the hydrogen here versus this hydrogen, then this hydrogen is more acidic. So removing this hydrogen is much easier. So therefore, if you compare rate of enolization, R2 is greater than R1. And that is kind of helping the reaction to happen again. So this enolate will form even better compared to the first enolate ion. And now again, when you react with one more mole of Br2 and Br2, I mean Br and Br here, so this minus charge will attack, Br would leave, and that makes it 2Br group, 2Br group and CHO. So from here we can say when it comes to base catalyzed mechanism, you can replace all the hydrogens present on the alpha position. Okay. So for instance, if you have double bond O here, and then I'm treating with Br2 excess and in NaOH, then what we can expect? We can expect that all alpha positions will be all alpha positions will be replaced by bromine. So this is a difference between acidic medium and basic medium. In basic medium, all of the alpha hydrogens will be replaced. Okay, and mechanism is also suggesting that. So let me give you more compounds like that. Double bond O here and pH here, like this. So it doesn't matter if we have Cl2 in excess with, let's say, I have calcium hydroxide, like this. So here also, we'll first write the structure given, then replace all the hydrogens possible with chlorine. Here, this is the product you will get. Got it? See the next, another important point here, very important point here. Note this down now. That is, if you have, let's say, uh, double bond O here, and let's say this is the way it is given, and I'm treating this with Cl2 and NaOH, but this time, what if I restrict this as only one equivalent versus one equivalent? So I'll write down that as one equivalent. So Cl2 also as one equivalent. Okay, hear me out carefully. When such cases are given, correct? See, imagine one molecule at a time. One molecule, not one mole. One molecule. The first molecule of chlorine will go and make an attempt here. Why? Because this side, the carb anion is more stable than this side. So the first molecule approaching the first molecule here, and that will make minus charge here. And that minus charge would take one chlorine and you'll get first chlorine here. Everybody, the first chlorine will come here. Well, that's good. First chlorine is coming here. But now the second molecule is approaching. When the second molecule is approaching, if you have to notice the enolate form of this and enolate form of this one. The enolate form of the first one is like this. The enolate form of the second one after chlorine is this way. Now you know that this enolate form is easily forming, correct? This enolate form rate versus this rate, you know that this rate of enolization is faster. Hence, the next molecule of Cl does not go to this one. Instead, it will go to this one. So now the second molecule as it approaches, now where does we get here? So here two chlorines would be coming, correct? Now two molecules have been done. Remember my part, two molecules have been done. Now if you keep doing one more time, the next molecule will not go on to these cases now, neither here, nor here, nor here. Now it will take up the route where, so I mean, neither this nor this, but it will go to this position. Hence, now I'll get one chlorine added here. Correct? So like this, with one chlorine added here. So have you noticed something? That means after the first chlorine is substituted, we do not have any role for this one. Now the role is only about this one. And this, after one chlorine, now this is not, after two chlorines, now the third chlorine will be based on this one. And we do not have any role for these two. That's the reason why you would notice that whenever a chlorine is being added here, or halogen is being added here, you need to imagine as if all these chlorines would utilize every location possible with one molecule only. So which means you will always report the product as chlorine, chlorine, and chlorine like this. Okay? So the balanced equation here, you need to change this balanced equation first. So that means since three chlorines are required, so this is a balanced equation now. Plus how many moles of NaBr here? So 3 moles of NaCl will be formed. Got it? Now check out which is limiting. Correct? So unless that, you do not judge limiting just on the basis of the first given equations. So now one equivalent, one equivalent. So you require actually for n one equivalent, we require 3 chlorines, but how much it is given? One equivalent. So this is limiting. So this is limiting. Since this is limiting, for every 3, I'm supposed to require 1. So for every 1, how much will be required here? 1 by 3. So this will be only 1 by 3 done. So 2 by 3 is left over. This will be left over. And how many moles of this will be formed? Only 1/3 of the mole formed here. Clear? Very important. This idea has been asked in JEE Advanced multiple number of times. So learn that what kind of a ratios will give you what product. Please do check. If anybody has a doubt, they can ask me now. See, haloform reaction is a special case of what we have just discussed. That is, here, imagine if I have CH3, C double bond O, CH3, correct? And then if I react with Br2 in the presence of NaOH, what would you expect here? And I'm taking in excess, imagine. In that case, I'll expect this as Br3, C double bond O, CBr3. Okay? But this is not exactly what is forming. Correct? Instead, the reaction is going like this: CH3, COO minus Na plus CHBr3. Now, this is what is forming. Correct? So, we are expecting this. This is expected, but this is actual. Actual, this is what is happening. We know the fact that the first 3 bromines here, let me write down this way as a mechanism part. You know that up to the first 3 bromines, you know what will happen. So this will be CH3, C double bond O, CH3 plus 3 moles of Br2 in the present with 3 moles of NaOH. If I put it so far, I would know that first 3 would be replacing all the hydrogens here and you'll get this as CBr3. Correct? Up to this, there is no problem. So 3 NaBr. Now, problem starts at this position. Once you get this position here, now OH minus was actually trying to go fetch here, proton here. But it realizes that OH minus will now can be acting as a nucleophile. So instead of acting like a proton to extract this H plus, now it will act like a nucleophile and make a nucleophilic addition reaction. So now you will notice that NAR, nucleophilic addition reaction, will take place and you will see that CH3, CO minus, OH and CBr3 will be formed. What was the reason for doing it is that this CBr3 is a very good leaving group. So as it leaves here, so now we will get this as CH3, C double bond OOH plus CBr3 minus. Okay. And you can see these two are like acid and base. So CBr3 minus will take H plus and convert this to CH3, COO minus plus CHBr3. So since it is a bromine based halogen here, trihalogen, you call it as bromo form. If it is any other halogen, it is called halo form. So what is the condition? What you notice here is that when you have a CH3 here, after replacing everything, if that becomes a good leaving group, then the next OH minus, instead of acid base, it will make a nucleophilic addition reaction. Overall, it is not nucleophilic addition. If you notice that first addition has happened and now elimination has happened. So overall, what is the type of mechanism here? It is SNTD. TD means tetrahedral formation, or SNAE, addition followed by elimination. This is a mechanism that has taken place. I hope you guys understood that. So if you remember, we did the halogen reaction before. This is the same mechanism we did this before, right? So this is how the haloform would come across. Got it? So what are the conditions we learned just now? Okay. Open alpha methyl, open alpha methyl, okay, or alpha active methyl, sorry, alpha active methyl between two carbonyl groups, between two carbonyl groups will help in getting haloform, haloform reaction. Okay, let me show you one examples here. So first simple examples here. For example, if you have ketone like this, and then you are reacting with, I'll write the exact moles also. So let's say 3 moles of X2 plus 4 moles of NaOH. That will be sufficient enough to make the reaction as double bond O with O minus Na plus, and 1 mole of CHX3 and 4 moles of, sorry, 3 moles of NaX. So this is the overall reaction. Okay. So you can have the phenyl group also like this. Suppose I have phenyl ketone this way, and that when you react with CaOCl2, this is another way of representing. Instead of writing it as chlorine in NaOH, we can write it as CaOCl2 aqueous. That will give the same role. So CO twice calcium plus, and here we'll have CHCl3. This is a product form. Done. So you can see chlorine in NaOH, or CaOCl2, or CClO3 plus KClO3 plus Cl minus in basic medium NaOCl. All of them represent that we are getting a Cl plus out of it, and that will help in making an halogenation form. Okay, one second. Done. Right. See the reagents here. All these are the reagents which you can do it. Clear? Notice one important aspect here, that is, in case if we have a CH2 here, that is at alpha position, and that same alpha position, there is an electron withdrawing group. How are the electron withdrawing groups? Like this: NO2, COOR, CN, CONH2, SO3R, NR3 plus. If these kind of withdrawing groups are present, correct? These withdrawing groups would make the halogen to first forcefully come at this position. Even though there is a methyl here, halogens does not go there. So, clear? In that case, here, in such cases, no reaction will take place. Okay? Let me show you in this case here. Check out. If you have NO2 here, for instance, OH, my first two iodides will attach on this position, iodine and iodine here. Okay? And after that, the OH minus will go act like a nucleophile, try to get added, you'll get this form, and that O minus will push and try to get a minus charge here, and this is what will come out. NO2 minus will take H plus, and this is not a halo form. I hope you guys understood that. So even though there is a methyl here, we will not be able to get halo form. So just having a methyl, alpha methyl is not sufficient condition to get a halo form, okay? Because this kind of a problem will arise. Even though there is a methyl on this position, we can always have some iodide form and we can get this product. Clear? So I hope all of you understood this logic, right? But now both sides, if you have ketones or both sides, if you have aldehydes, right? Or combination of any of these two, aldehydes and ketones, any of these combinations, if you notice, in such case, you will see that we will be able to get the haloform reaction. Check out in here. One second. See, if you notice that here, first we'll get iodide and iodide here, and then the second OH minus will go from here. It will make a nucleophilic addition. Then the elimination, push here, iodine is removed. So this side you'll get an acid. And look into this part now. So Ci2 minus and CHO which is present, the Ci2 minus will take H plus from here. You will get a formate ion and this part will become CHI2CHO. Now this you can discard, but this you can still continue, right? Because this again, if you continue with iodine, even this hydrogen will be replaced by I3 and then OH will again do a nucleophilic addition, then elimination and Ci3 will come out and it will take H plus, convert into halo form. If it is iodine, it is iodo form. So I guess all of you understood this point, how you get an halo form here. Okay, which means if both sides, if the active methylene, this CH2 group, is between the aldehydes or ketones, okay, between the aldehydes and ketones, you will always get the haloform or positive haloform test. Okay, so notice this one. First, I2 and NaOH. Check here. This is carbon 14. That is what we need to do. So simply write this as the product here. Like 2 moles of CH3CO minus will come. And that carbon 14 one will convert into iodo form. This is a product. And you know, when it comes to iodo only, it is a yellow color PPT. Next, second one also. You will get this as COO minus here. And here also you'll get COO minus. And that middle carbon will convert into CHI3. Here also. Now, here this is not a ketone, everybody. This is an ester. So, since that is an ester, this side you will get an acid, C double bond O, O minus. On the other side, I'll get this as RO, C double bond O, CHI2. That's it. This is the precipitate what you'll get. But this is not haloform. So, this is negative haloform test. Negative haloform test. Okay. Now, if there is no active methylene here, then there is no problem. You can take any one side and convert that into haloform. So I can get this as CH3, C double bond O. The next carbon will become C double bond O, O minus, and the last carbon will become CHI3. Here, this side you already have an acid, this side ketone. So there is an active methylene here. Sorry, there is an active methyl group here. So that will convert into CH3I plus COO minus and COO minus. Here one side C double bond O is there, that will become CO minus, and this will become CHI3. Okay. See, in this case, after making a phenyl, because these are very bulky enough on this position. So once you get C double bond O and CI3, now further movement of OH minus is very difficult here, and it will get precipitated here itself. So no haloform in this case. No haloform reaction. So haloform product. Correct. Next case, we can always get haloform easily in this case. So we can get CO minus and CHI3. Next. Listen, if you have alcohol also, okay, if you have an alcohol also, then also you will get the product. That is, if you have OH and CH3 here, first O will attach to iodine, hydrogen is here, then OH minus will take the H plus from here, that will push here and iodine will come out. So this way you are first generating a ketone. That means alcohol will get oxidized in the presence of iodine, convert into ketone, and from the ketone onwards, you know the reaction. Again, it will take 3 moles of iodine. Here it took 1 mole of I2 and NaOH, and here you take 3 moles of I2 and NaOH. Got it? And then what is the product you will get? Same thing, O minus, Na plus, and this would be CHI3. Okay, please check out the examples quickly. If there is a doubt, you can ask me. Next, check out this ethanol can easily convert into acetaldehyde, and acetaldehyde will give you positive test. Here, this will also convert into a ketone, and that ketone will give positive test. Okay. Here also, first ethyl chloride will convert into ethanol because you are treating it in NaOH. That ethanol will convert into acetaldehyde, and that will give you positive test. So here also same thing. First it will convert into alcohol, and that alcohol will convert into an ketone by oxidation, and then you will get positive test because there is a methyl group on it. This will any give positive, positive, and positive. Okay. So all of these will give positive haloform test or positive iodoform test. Next. Notice what is alpha alkylation. We know that when you react with a base, you will always get a carb anion here at alpha position. And these carb anions, everybody are very good nucleophiles. So since they are good nucleophiles, those nucleophiles can make some kind of SN2 attack. So as long as this alkyl halide is good enough to carry on SN2 mechanism, the reactions can take place like this. So mechanism wise, if I write this, check the keto part here. When you react with some base like OH minus, it will extract the proton and get into an enolate ion. And this is a good nucleophile or a strong nucleophile here. So that when you react with Rx here via SN2 mechanism, so via SN2 mechanism, it will convert into R here plus X minus here. So this is the product you will get. So this kind of a substitution is what we call it as alpha alkylation. This is called alpha alkylation. Okay. Now, what we have to understand for alpha alkylation is these 2 points. Check out. One, suppose if the alpha halogens are of two different kinds, that is, one is 1 degree, the other one is 2 degree. Now, what I can say, if the hydrogen is being extracted, so first imagine if the H plus is being extracted from here, so then you will get this as the intermediate, which is the enolate ion. Or if H has been replaced from here, then this as the intermediate. So these two are the intermediates which we can get. Okay. So from this intermediate, I mean, if you compare the stability of these two intermediates, we can say this is 1 degree carbanion. So this is more stable than 2 degree carbanion. So the intermediate is more stable here. But if you write its double bond form, that is in an enolate form, the alkene enolate form, this is called alkene enolate form. In alkene enolate form, this one is more stable, correct? So that is because you have two methyl groups here, both can give almost 6 hydrogens of hyperconjugation. Here you will just have 2 hydrogens of hyperconjugation. So definitely this one is more stable in terms of its double bond form. So the one which is more stable in a double bond form, that is the more stable in double bond enolate form, that is called as thermodynamically driven product, TCP. And the one which is forming as a stable intermediate, initial intermediate, that is called KCP, kinetically controlled product. Okay, clear. So now, usually what would happen if a base is going, it has an option to either take H plus from here or to take H plus from here. In case if the base is very bulky, like tert butoxide, LDA, LDA is also a base, R3N, these are all bulky bases. When you take bulky bases would like to extract only from the less substituted carbon side, which is this one. So you will get a KCP based product. While if you have a smaller basis, strong basis but smaller basis, then they will be easily extracting proton from here. Why would they prefer here? They are not looking in terms of which hydrogen to pick. These bases are strong enough to pick both of them. They can easily extract both of them. So if competition is not about picking hydrogens here, it is about who can make more stable double bond. So this small bases will always be excited to get a more stable double bond form. Okay. So this is KCP and this is TCP product. Hence, if I put some examples here, you will understand it better. Suppose I have double bond here and a methyl here. And this I'm treating with LDA at minus 78 degrees Celsius. That is followed by CH3Br. Then what is the product I will represent here? So I'll write this as double bond O. You know that this hydrogen removal is more observed when you use LDA. Therefore, that is the direction where you will write the methyl here. So this is major product, correct? But if I take the same reactant here, but this time I'm taking this as NaH in hexane, okay, at normal temperature or room temperature, or temperature is not even mentioned. And then I'm treating that with CH3Br. So this time the product what you will get, the major product will be methyl and methyl. So this is major. The first one is based on the stable intermediate. So this is called KCP. Second one is based upon stable double bond, enolate. So that is TCP. Correct? So you should be able to figure out which case it is KCP, which case it is TCP. Please check everybody. Okay. Now there would be an example. We can always have examples where both KCP and TCP are same. For example, here If I take a double bond O and double bond O, I have two types of alpha, this one and this one. Of course, this alpha and this alpha are same. So I'm considering two distinct alpha, this one and this one. But you see, when you put a double bond here, that will get a extra conjugation also. So that means double bond is also more stable, and this is an active methylene position. So carb anion is also more stable. So both KCP and TCP are same. So it doesn't matter what you react with. So suppose if at all I react with NaH or LDA both will give you the same product only. I mean same intermediate only. That is double bond O and minus. And if this you react with something like CH3Cl, in that case you will get that CH3 substituted here via SN2 mechanism. Correct? This is the one which you will get. Another example, suppose if you have a double bond here, double bond O here, and OET is present. OET is there. And I use this as ETO minus. ETO minus is also a strong base. It will extract the proton from this position. That is an active methylene position. And then imagine you react with ethyl bromide. Then we can say that ethyl will get substituted here like this, and OET will form. Now see what I am doing. Most of these questions are always followed by hydrolysis. And you know that ester will undergo hydrolysis to convert into acids plus ethanol. Okay, this is the compound we have. And now check this compound carefully. This is a beta keto acid. So this is beta keto acid. And if you may recall, beta keto acids on heating, just on heating, it gets decarboxylation done this way. And you'll get this as hydrogen here and CO2. Okay. So this part of the ethyl is this part. And this part, this CO2 has gone here. That is released out. So this is the product you will report. This is the product we will report. On similar lines, I'll give you one more example. Please check this out. Suppose I have phenyl and I have double bond O, and O with isopropyl here. Okay, this way. And now what I'm asking you, you react this with isopropoxide like this, isopropoxide followed by CH3I. So that is clear that first this isopropoxide will take H plus from here and that will go attack CH3. So first product what you will get here is double bond O, double bond O. This isopropoxide will be here and CH3 will form. And I am doing one more time the same job, that is O minus followed by CH3I, correct? Because one more hydrogen is still present, that is also still acidic. So as you do that, you will get double bond O, double bond O, one more methyl will come here and isopropoxide will be here. Now normally in the questions, it has been said that this will get two products on hydrolysis. So let's say on hydrolysis, we will get this as pH, double bond O, double bond OH, and here we'll have two methyl group. That plus propanol. Correct? So let us call this as compound A and B. Let's say A and B. A lot of times in the question, it will be asked that after this, heat is been done. On heating, correct? Just heating. Just heating, this B will not change, but A will change here now. So you will get this as double bond O and this plus CO2 and that B will remain, correct? Now, if at all you react, because CO2 will anyway evaporate out, And if you react with this Br2 and NaOH, correct? Br2 and NaOH, this can be separated out and it will be asked like B is reacting with this one. Will be. In that case, the B will become first a ketone, correct? If you take one equivalent, and that Br2, if you take excess or three equivalents in NaOH, this will be haloform reaction. So you will get this as double bond O, O minus and CH Br3. So this sequence of reaction is very, very, very important in JA. Okay. So you should know how we start with the active methylene positions, keep substituting multiple number of times S by SN2, then hydrolysis, then heating, and from there, if there is an extra product, that extra product information will always be mentioned. Please check quickly. See the next example. LDA minus 78, N-hexane. This is given. You know that LDA would definitely take away proton from here and that internally attacks because SN2 happens internally this time. So what is the ring size? 1, 2, 3, 4, 5, 6. So you will get a product like this. 6-membered ring this way. What about in the second case? NaH and hexane here. So this time H plus will go from here, minus will come, that minus will attack. 1, 2, 3, 4. So you'll get product in the 4-membered ring like this. And here we have double bond O methyl. So this is a product form. Yeah. Hmm? All good, guys. So check out. In your pre-notes, you will have this sixth reaction as alpha nitrosation. I just pushed it a little down. So you can start from here, alpha nitrosation. Alpha nitrosation is a very simple reaction. You know, if you remember that when I take NaNO2, add it to HCl, correct? So that will convert into HNO2 plus NaCl. HNO2 is a very unstable acid, especially in acidic medium. It will convert into H2O plus NO plus. And NO plus is an electrophile. Okay. So that electrophile can be used in alpha nitrosation here. Okay. So that is if you have double bond O here and as you treat with NaNO2 in HCl here, so that will convert into double bond O and NO. That would be in equilibrium to get this as double bond and double bond N and OH, which is stable because you'll have an extended conjugation here, correct? You know that this is nitroso and this is oxime, and there is a tautomerism happening, so that is why it is called as nitroso oxime tautomerism. Okay, mechanism is very simple, that where you have double bond O in acidic medium, in acidic medium you first write it in an enol form, and then N double bond O plus is there. So this lone pair will try to push it to take NO, and that will make it double bond OH plus, and here we'll have NO. Okay, and that eventually will convert into OH with N double bond N with OH here. Sorry, this will be C double bond O. Okay, so this is how the reaction takes place. So alpha nitrosation is a simple reaction. We will report the nitroso product only when we have like this. Suppose here, if at all I react with NaNO2 with HCl here of, let's say, one equivalent. In that case, because it is in acidic medium, you'll always have to write substitute in the direction of more stable enol. So based on that, more stable enol is on this direction, so NO will go here. But unfortunately, there is no hydrogen here, so only this is a major product you will report. So this will have no oxime form. Since there is no oxime form, you'll only report the product as nitroso. Okay. Yes, everybody's clear on that. Right, guys. So we'll stop it here now.